Hey everyone, my name is Aditya Raj Rijit and my registration number is URK23CS1010. Today we'll be having a look at experiment 4, which is single layer perceptron. So we'll be building a single layer perceptron from scratch. So this is where we really understand how neural networks work at their most basic level. So we're going to build a perceptron that can classify iris flowers, specifically distinguishing between setosa and versicolor, using four features: sepal length, sepal width, petal length, and petal width. And we are doing this completely from scratch. So there's no SKL module. No, there's no. So we are not going to use SK learn for the model. So before we jump into the code, let's understand what a perceptron is. So think of it as the simplest possible neural network. So it just has one layer. It takes multiple inputs, multiplies each by a weight, adds them up with a bias, and then passes the result through a step function. If the weighted sum is greater than or equal to zero, we output one. Otherwise, we output zero. During training, we during training whenever we make a mistake, we update the weights to correct it. So it's simple, but it's powerful. So let's start with question one. Loading the data. I'm using pandas to read the iris underscore slp.csv file. You can see the dataset as columns for ID, sepal length, cm, sepal width cm, petal length cm, petal width cm, and species. So for question two, we perform pre-processing, and this is really important. First, I check for missing values and look. There are quite a few. Some are NA, some are zeros, which are probably errors since flower measurements can't be zero. I replace zeros with NAM first, then impute all missing values with the column name. Next, I need to encode the species for binary classification. We only want two classes, so I filter to keep only iris setosa and iris versicolor. I manually create a mapping, so setosa becomes 0, versicolor becomes 1. And this is manual label encoding without using any library. Moving on to question three, choosing our variables. So x is all four measurement columns and y is our encoded species. So question four is standardization. So this is crucial for our neural networks. So I wrote my own standardization function. I subtract mean and divide by standard deviation for each feature. And after standardization, each feature has mean 0 and standard deviation 1. This helps the perceptron converge faster because all features are on the same scale. So question 5 is basically train test split. So I do this manually using random permutation, 80% for training, 20% for testing. I use a random seed of 42, so results are reproducible. You can see the class distribution is balanced in both sets. Question 6. Question 6, it's basically about setting our hyperparameters. So learning rate is 0.01. This controls how much we adjust weights each iteration. Too high and we might overshoot, too low and training takes forever. Number of iterations is 1000. I initialize weights randomly using a small random value, 0.01 times random and bias to 0. Random initialization helps break symmetry. So question seven is basically let's see. First, I define a step activation function. It returns one if input is greater than or equal to zero, or else it returns zero. So this is our decision boundary. Then the training loop runs for 1000 iterations, and in each iteration, what I'm basically doing is first I calculate z, and then I pass through step function to get predictions. Then I calculate errors. I count how many misclassifications we have. I update the weights, and then I update the bias. So I print progress every 100 iterations, so you can see the weights changing and misclassifications decreasing. And yeah. So in question 8, it's basically about displaying final weights. Each weight tells us how important that feature is. Positive weight means higher feature values push towards class 1. Negative means they push towards class 0. I also show feature importance based on absolute weights. This tells us which measurements matter most for classification. So question 9 is basically about plotting iteration versus error. So this shows our perceptron is learning, and the number of misclassification drops quickly in the first few hundred iterations, then stabilizes. So this shows how perceptron is learning. Mm, So the error rate goes from maybe 30 to 40% down to near zero. So then for question 10, basically what we're doing is we are predicting on test set. So I used our trained weights and bias to predict on data the model has never seen, and I will show the first 20 predictions, actual versus predicted. Most are correct. You can see the check marks, and what this shows is basically first I build a confusion matrix manually. Then the confusion matrix, what it shows is true positives, true negatives, false positives, and false negatives. From these, I can calculate the accuracy, precision, recall, and a phone score. So, yeah, I've created several visualizations to help understand our model, such as confusion matrices for training and testing, then accuracy comparison, bar chart, matrix comparison, and so on. So that's it for this experiment. Thank you.